So talking about the partial volume effect, for example, that is when you have a voxel occupied with fibers with other stuff. So it could be edema, it could be some free water close to the ventricles of the brain, which happens already in the healthy brain. All of this is called partial voluming because the volume of the voxel is occupied by different tissues. So what can we do about that already? So obviously tensor-valued diffusion encoding was one good bit of what to do with that. And the good thing with tensor-valued diffusion encoding is that just by acquiring different kinds of diffusion weightings, you can already have some kind of better idea of what kind of microstructure you're looking at. So it could be, yes, I have fiber crossings, but instead of averaging everything on the whole voxel and do an FA measure, you can then do a micro FA measure that will be more sensitive to the fact that these fibers are existing, yet not coherent at the voxel scale. Doesn't matter. It could also be different populations of water, and it gives a pretty good shot at least trying to tease apart populations in a voxel. So that's why you would like to use it. You could also try to use multi-fiber modeling without even using tensor-valued diffusion encoding. I will cite one example that I know can handle crossing fibers, and I am still pretty sure it is one of the rare ones that will do it at that level. It's the diamond model. For example, if you take a voxel with two populations of fibers crossing in blue and orange, and you get this free water population in green, the diamond model will separate these three populations up to 3 fibers. You have a max of 3 fibers to make it computationally doable. And you could isolate the water population, but this is a free water population. So you have to fix the diffusivity to 3 micrometers squared per millisecond, and that's it. So that also will maybe give rise to some problems in the fitting problem. But then you can describe each of these fibers by a collection of diffusion tensors, distribution of them. And this is kind of cool because then you get all this wealth of information per fiber, and you can also tease apart crossing fibers right away. So actually I worked on this. I tried to extend this model to tensor-valued diffusion encoding at the time to be able to maybe refine this. It happens that this model seems to be already too constrained so that the tensor-valued diffusion encoding doesn't bring much to the table because of all the constraints that have to be satisfied by the mathematical modeling. But still, if you use that, you can get, for example, a set of peaks for orientations. So here, if I zoom on so this is called usually the centrum semi-oval or the corona radiata. It's 2 ways to kind of call it from different fields. So here we have this region, we have a crossing between the corpus callosum, the corticospinal tract, and maybe the arcuate fasciculus, and you can see this crossing just using the peaks with these different fibers from a very coherently organized fiber bundle, which is the one single fascicle corpus callosum, to this region of heavy crossings. And then you can do tractography with it. So that's one tractogram that I was able to tease out. So I was mapping something other than orientation on the tracks, but still you can see this CC, corpus callosum, and the CST, for example. So that's one way to go. The problem with this is that it is modeling. So it has assumptions by default, and then that may not work in a non-healthy brain, for example. This is very arguable that around the fiber, around the tumor, it will work because it may not satisfy the model's assumptions. So maybe we should not do that. Another way that is quite recent, actually, is Li Pengling that has done that, or at least published it this year, is to try to use kind of filters on the first moments of the probability distribution of diffusion tensors and T2. Actually, it's mostly diffusivities and T2, not tensors. But still doing that kind of stuff, you can see that, let's say, you have this ODF here in an area of crossing. Actually, you can try to get an idea of which fiber has a slow relaxation, slow R. So it seems that this is the CST going up, as a slow relaxation, so a higher T2 than these other fibers that are at fast relaxation. Actually, you will see in results that I got that this is something that becomes apparent now, that the CST has higher T2 values than other bundles in the brain. So this is one way that you can do this, but this relies on accumulant expansion, which also has limitations and may not work, especially in areas where you have crossing fibers because you have a lot of dispersion in orientation. So this is one of the limitations of the cumulative expansion. So maybe take this with a grain of salt, but still, this is very cool results, I find. And finally, the Monte-Carlo inversion, of course. So I will skim through it a lot because I know you already know a lot about this, but still, for different voxels, you can get these populations of points of solutions that are affected a certain d-iso, a certain d-delta or shape number. You have these colors for orientation, and you have the size of the circles that gives you probability weight to some extent, or at least signal fraction, or volume fraction in that case. So here you have, for example, an example with partial voluming. So you have some fibers from the corpus callosum, and you have this water population that comes from the ventricle, the vicinity of the ventricle. So then we just separate this, it's fine. You can also use binning. It was done by Joao and Daniel. That you can use binning also to isolate certain part of that space of solutions that hopefully will correspond and match a certain tissue type. So it happens that you have, for example, this thin bin, and I will focus mainly on that one because it's the fiber bin that takes all of these very anisotropic solutions and does correspond to white matter. The problem is that it is still very sensitive to noise in the data, as that's something that I showed in our paper at the beginning of the year in NMR Biomed. And the thing is that to mitigate this, because of course you have very little, if not none, no approximation whatsoever or assumption made. So of course it's going to be sensitive to noise. You have no constraint. But one way to constrain naturally, let's say, this inversion is to just optimize the acquisition scheme, or acquisition protocol. And there's been very little work on this for non-parametric signal inversions. If you have a model with parameters, then we have mathematical tools to do this. And it's become quite trendy these days. But for something non-parametric as the Monte-Carlo inversion, not so much. And the final part of the pretty much presentation is how to go down to the fiber level. So I will go down to the fiber level via the Monte-Carlo inversion, because modeling has limitations. Cumulative expansions has limitations. So you don't want to maybe go for that one if you can make something work for the Monte-Carlo inversion. So these ODF stuff that I've been showing since the start can actually be obtained with the Monte-Carlo inversion. So you take the weight of your solutions, you take the unit orientation of the solution, and you can use, for example, this Watson kernel. There is it's a famous distribution of orientations on the unit sphere, but in that case, it's just used as a smoothing device because you have a discrete set of points, and you just want to make it slightly more continuous. And this is just a basic smoothing. It's fine to use that. So you get, for example, this kind of ODFs. And this is an axial slice, so seen from the top. And you can see the corpus callosum here. You can see maybe the fornix here that is below the corpus callosum. I didn't show it to you before. You see the CST, corticospinal tract, in blue going up here. And you see this, I think this is the arcuate fasciculus going on the side here in green. So it gives pretty much the right thing. And you can also map matrix on top of this. So this is an anisotropy of the fibers, which looks pretty smooth, pretty uniform within the white matter, except when you get close to water in other, like the edge of the brain or the ventricles. And you have this R2, which is 1 over T2 in that case, also can be mapped. It seems to be rather uniform to some extent too, at least on this map like right now. And this is the map showing where you have non-fiber populations, and it actually shows you that even in voxels where you have partial voluming, so you have other stuff than fiber in there, you still get ODFs, it's fine. So that's pretty encouraging. So with this ODF, you can use that already for tracking if you want. We can feed that with spherical harmonics if we want, and then readily input this in tracking algorithms that already do exist. We can use the peaks of the ODS for other kind of tracking strategies that exist. So that's cool. We can get these ODFs, we can get the peaks, and we can even get the metrics associated to these peaks, like the ISO, d delta squared, and T2. From this ODF that joins the corpus callosum, the arcuate fasciculus in green, and the CST, or corticospinal tract, in blue, you can see that the corticospinal tract seems to have a higher T2. We already saw that a bit in Li-Peng Ning's paper. It was also shown in the last paper from Bien Lampinen, that T2 seems to be higher. The problem with this is that it's hard to actually say what's the error bar on this point, like what's the actual statistical value of that metric. So I call that not properly quantifying things. So it is a very convenient way to have a coarse-grained idea of what's going on, but then if you want finer details, you need something more.